Hello everyone, welcome to a new lecture of our course on heterogeneous systems. Today we are going to start talking about GPU programming for general purpose applications. In particular, we are going to start with the basics of the GPU software hierarchy, and we will define what's a grid, a block, or a thread inside the GPU programming model. We will focus on CUDA because that's the, let's say, the mainstream GPU programming framework, but anything that we describe or discuss today will have its counterpart in the OpenCL programming language. Before we go into the detail, let me very briefly remind you what we covered in our previous lecture. We were talking about the architecture, or we started to introduce the architecture of SIMT processors and GPUs. And at the end of the presentation, I told you that at the end of this course, you would be able to understand the most inner details of this NVIDIA A100 GPU. Remember that it's a GPU with 108 cores in the A100 version. And remember as well that inside the A100 core, the GPU core, we can identify different functional units that remind us what a SIMT processor is. It's not the only thing that GPUs share with SIMT processors in the way that we explained them in the previous lecture, because also GPUs use banked memories that we also introduced in the previous lecture. As an example of banked memory, in this A100 core, we have this shared memory. Remember as well that I showed you this slide where we see the evolution of NVIDIA GPUs since 2009. Actually, CUDA started like 2-3 years before 2009. In 2006, 2007, we had the first CUDA-enabled GPUs. And since then, we have seen very fast increase in the number of functional units and the processing or the computing power of the GPUs in gigaflops until this A100 architecture from 2020. But these are not the only NVIDIA GPUs these days, because exactly this week we learned about the new GPU from NVIDIA, which is the Hopper architecture. As you can see in the slide, significant increase in the number of functional units and significant increase in the peak gigaflops with respect to the previous generation, the Ampere. It's named Hopper after Grace Hopper, who was an American computer scientist. And this architecture includes several new innovations that some of them we will discuss over the course of this course on heterogeneous systems. But here you have the block diagram of the H100, where you can see up to 144 cores in the full-blown GH100 chip, and up to 60 megabytes of L2 cache, as you can see here in the middle of the block diagram. Observe as well other innovations and changes with respect to the previous architecture. For example, the PCI Express interface has been updated to the 5.0 version. The previous generation was 4.0, and now we have the 3D stacked memory that is connected to the GPU. It's now HBM3. It was HBM2 in the previous generation. We will talk later in this course about specific innovations in this architecture. I just want to give you a very brief announcement and introduction to it. This is the H100 core, where same as in the previous A100 core, we can clearly identify execution units for 32-bit integers, for single precision floating point, for double precision floating point, and the tensor cores that also have some novelties. For example, now they support 8-bit floating point multiply and accumulate operations, and actually they support 2 different formats of 8-bit floating point. Remember, even though this new architecture looks fascinating, we already know the basics of how it works. Remember that GPUs internally use warps, and they execute instructions for different warps in an interleaved manner, in a fine-grained multi-threaded manner. The good thing of using this fine-grained multi-thread technique is that it's possible to hide long latency operations, such as accesses to the external off-chip memory, or some execution of instructions, for example, transcendental functions that are executed in the special function units, and they usually take longer than the execution of integer or 30 or floating point multiply accumulate operations. Remember as well that the way we execute one warp on the GPU hardware inside the GPU cores also depends on how many functional units we have. And actually we talk about the execution of instructions from warps, same as we talk about the execution of SIMD instructions in SIMD processors as in a way that we can exploit the parallelism in either time and space, depending on what's the number of functional units that we have. And when we talk about a functional unit, we mean all execution units that are available to execute specific instructions in the SIMD hardware or inside the GPU core as well. We may have several of these functional units, same as we have just seen in the core of the H100 GPU. But yeah, and some of these functional units have different functional units may have different purposes. Here we can see functional unit here, and we also see a different one here. And also we have the partition register file where we have like the whole amount of registers that at the beginning of the execution are partitioned and assigned to the different threads that are going to run inside the GPU core or inside the SIMD processor if we are talking about SIMD processors. And remember as well that these combination of registers assigned to individual threads plus the corresponding execution units inside the different functional units where instructions from different threads are executed are called a lane. So every time we talk about the internals of the GPU core and how the warp instructions are executed, we would be talking about every single thread of a warp being executed on a SIMD lane of the GPU core. And as I said before, depending on how many threads we have inside the warp, and also how many execution units we have in each of the functional units, we can have more or less threads being launched and executing the instruction at the same time. In this slide in particular, we assume that the number of threads per warp is 32, and we assume that the number of lanes is 8. So what that means is that in every single cycle, we can start the execution of one instruction per 8 threads because we have 8 lanes. One cycle later, we can start the execution of the next 8 threads of the same warp. And that would apply to the different execution units that we have in our functional units that we have in our GPU, like load units, multiply, add, depending on the internals of the GPU core. They might be integer or 32 floating points, 64-bit floating point, etc. Okay, after very briefly reminding you what's the introduction to the GPU architecture that we covered in our previous lecture, let's start with GPU programming. As I said in the beginning, let's say, most popular and dominant programming language in GPU programming is CUDA, but OpenCL is also widely used, and it has certain advantages. The fact that it's cross-platform or multi-platform, the same code can run on different devices like NVIDIA or AMD GPUs, for example. And in the end, all concepts that we will explain for CUDA also apply for the OpenCL programming language. Remember as well that one important thing when it comes to using GPUs and SIMD processors is programming them in a way that is like relatively easy to handle by programmers or by compilers. Because remember this paper from Fisher in ISCA 1983, where he said that one of the biggest disadvantages of SIMD processors was the difficulty to map data and to map the data structures onto the hardware and to map the computation onto this hardware. One good thing of the general purpose computing on GPUs these days is that the learning curve and the difficulty to program these SIMD processors has been much alleviated. As I may have mentioned before, the GPU computing era started sometime in 2006 or 2008, and it became quickly very popular because it was a way of democratizing high performance computer. Because now anyone could have in their commodity PC a GPU providing a large amount of gigaflops that were not available a few years back. Yeah, and actually using these processors makes sense for many important workloads, because many important workloads exhibit inherent parallelism. If we look at matrices, if we look at images and image processing, or more recently, we look at deep neural networks, we will see that there is a lot of inherent parallelism, and in particular, a lot of data parallelism that is best suited for GPUs architectures. And but as I said, and as we have seen in the previous slide, programming is not for free. I mean, this is not for free. We need to learn how to program this new architecture. The good thing is that this programming model is now much more easy to learn than what we had in the past in, let's say, old SIMD processors. That doesn't mean that we have to rethink the algorithms and how we implement them on this new hardware. And still there will be some bottlenecks. It's not just exploiting the available parallelism and everything will be fine. There will still be some bottlenecks. Over the course of this course, we will talk about data transfers between CPU and GPU, even though PCI Express bus or NVLink have improved the bandwidth of communication between CPU and GPU over time. That is still far from the DRAM memory bandwidth, from the bandwidth to the external of chip global memory. It is a name that we will normally use in the context of GPU, and even so, the bandwidth of this external memory is also going to be important bottleneck because it's in the end small as compared to the large processing power that the internal GPU cores have. Okay, and we are going to start talking about the basics, as I said, the basics of the GPU software hierarchy. But before that, let me recommend you one book, Programming Massively Parallel Processors by Professor Wen-Mei and David Kirk. In the slide, you see the cover of the 3rd edition released in 2017. As far as I know, there is a new version, a new edition in preparation. The 4th edition hopefully will be will be released sometime soon in this year. As soon as I know something, I will let you know. And also another important reading, another important recommended reading, if you're going to program GPUs, you will have to go to the CUDA programming guide from time to time to clarify, for example, how different instructions are used, what's their syntax, and so on. It's definitely a key reference for anyone programming NVIDIA GPUs. And if you go to this programming guide, one of the first figures that you will see is this one, is that this simplified representation of a CPU and a GPU for us to understand very quickly what are the key differences between CPU and GPU. They have different design philosophies, as you see. While a CPU has very few out of order cores that are super powerful by themselves. GPUs have many more cores that normally are in order and fine-grained multi-threaded and much less powerful than each of the individual CPU cores. The biggest advantage is that we are going to have many of these small in-order cores, and this way we are going to be able to exploit a lot of parallelism. Besides the processing elements themselves, we also see differences in terms of how much area or how much space in the die is devoted to control, to internal on-chip caches, etc. We usually, we will normally see much larger caches, for example, in CPUs than in GPUs, even though the cache size, as we have seen in the A100 and the H100 GPUs, have increased, their size has increased a lot in recent years. Okay, very basic start of how to do GPU computing. Remember that we are talking about an heterogeneous system, so there is no GPU replacing a CPU completely. We assume that the GPU is a coprocessor or an accelerator that works together with the CPU. So computation is going to be offloaded to the GPU when the CPU decides. And we have three main steps in this process. First of all, especially in the case where we have discrete GPUs, which are the most powerful and also most popular ones, we'll have to transfer the input data from the CPU memory to the GPU memory. And once this transfer has finished, we can start the execution. We can start using the GPU cores. On these GPU cores, we run one function, and the name of this function is kernel, GPU kernel. After the kernel terminates, we normally retrieve the results. So read the output results from the GPU memory to the CPU memory. So this is the, let's say, the third step in this generic representation of the offloading to GPU. But how do the programs look? Let's take a look at the traditional program structure. We have CPU threads. We are going to assume that we have CPU threads running on the CPU, and we also have GPU threads running on the GPU, executing GPU kernels. We normally start the execution on the CPU, where we are going to continue executing those parts of the program that are sequential or modestly parallel, while the massively parallel sections of the code will be executed on the GPU. So we have maybe one or maybe very few threads running on the host, probably executing, as I said, serial or sequential code. And at some point, we will reach to the massively parallel section. And what we do, or what the CPU main thread does, is launching the kernel onto the device, onto the GPU, to start the execution. The way of launching this kernel is by using a syntax like this. Notice that this is kernel A. These are the input arguments here. And here in the middle, we have what we call the execution configuration. This execution configuration essentially determines how many GPU threads we are going to use in the execution of this GPU kernel, and also how these GPU threads are grouped. Because as we are going to see today, GPU threads are not simply launched onto the hardware. They are first grouped into thread blocks, and these thread blocks, when it comes to executing the code on the GPU hardware, are going to be mapped on the GPU cores. So here you see more or less a representation of, it's called a grid of threads that run on the GPU to execute this kernel A, and these threads are grouped into thread blocks, as you can see here in the figure. At some point, the kernel will terminate, the control returns to the CPU, to the main thread in the CPU, and sometime later we will reach another massively parallel section, and now we have to execute this kernel B. Again, we will use certain number of blocks each of a certain number of threads, we launch the kernel and start the execution on the device or GPU. This is what we call or inside the GPU, what we use is what we call the SPMD programming model, single procedure or single program, multiple data programming model, where each processing element executes the same procedure except on different data elements, and they can eventually synchronize, also we will see. Using barriers, we call them sync threads in CUDA, as we will see soon. And essentially, each procedure is a different GPU thread inside the GPU. Each of them executes their own instruction stream, execute the same program, but they operate on different data. So they have this ability to work on different data, and they also have the ability to execute different control flow paths. And that's something that we described in the previous lecture. We talk about the conditional execution, we talk about the use of masks and how these masks allow us to have different threads belonging to the same warp to diverge and execute the corresponding control flow path. That's important, it's useful in terms of programmability, but it's also important and necessary to understand that this divergence is not desirable if we really want to maximize the performance of our programs. We will talk about that, and we will have time to go in depth on how to optimize code in this course. So the SPMD programming model is the programming model of CUDA and OpenCL. Besides this characteristic of using multiple threads, multiple procedures, executing the same program on different data, another key characteristic of this programming model is that it is bulk synchronous programming. What that means is that at the end of one kernel, there is a global or coarse-grained synchronization. And what this means as well is that if we have two different threads or two different blocks executing on our device, we cannot be certain about when these blocks are exactly going to be executed. The only thing that we can know for sure is that at the end of the kernel, when this coarse-grained synchronization happens, all thread blocks that have executed the kernel terminate, and at that point, we can assume that all the previous computation has been done. As I said before, and as we have just seen, the host still controls the execution of the program, and this host, that is typically a CPU, allocates memory on both the CPU memory and the GPU memory, moves data between the CPU memory and the GPU memory back and forth, and also launches the kernels as we have just discussed in the previous slide. And the device, which normally is a GPU, executes the kernels. It's important to highlight here that when we talk about the device, we will be talking about the GPU, because, for example, the OpenCL programming model, the OpenCL programming language, is not only useful for GPU computing. You can also use OpenCL to program FPGAs, for example. And in that case, the device is not a GPU. The device is an FPGA. But the programming model and the way of programming the system is exactly the same. When it comes to executing a kernel, the whole group of threads that we launch onto the GPU hardware is what we call a grid. So that's the total group of threads that execute a kernel. This grid in OpenCL is called ND range, but it's essentially the same. As you know, the threads are grouped into thread blocks, and these thread blocks in OpenCL receive the name of work groups, but they are exactly the same. Inside one block or inside one work group, we can share memory. We can easily communicate using the shared on-chip memory that each of the GPU cores have. And it's also possible to synchronize. We will see how. I already mentioned the barriers and the sync threads. And finally, the lowest level of this hierarchy, we have the threads or work items in OpenCL that are those procedures, those threads, software threads that are going to be mapped to a SIMD lane and are going to execute their own procedure, their own program. So going back to, well, continuing with the traditional programming structure in CUDA, we are going to see a little bit of code already. We will have function prototypes for the CPU functions. They will keep being the same as usual. In the C function declaration can be, for example, this one, float serial function with its own arguments. When it comes to declaring the kernels, it's a little bit different because in this case, we have to use this global qualifier that will tell the compiler that this function prototype corresponds to a function that executes in the GPU, so a GPU kernel. But we would still have a main function that will run on the CPU. And as I said before, the CPU thread will have to allocate memory on both the CPU memory and the GPU memory. And notice that you can clearly see what this means. CUDA malloc is a malloc, so it's an allocation, memory allocation operation that happens on the GPU, and this corresponds to the CUDA library. Then we also have specific functions to transfer data between the host and the device, between the CPU memory and the GPU memory. And this is the most common one, is the CUDA main copy library call. Then we need to define what's the execution configuration, what's going to be the number of threads per block, and what's going to be the total number of blocks that are going to compose or grid. And then we call the kernel using the, we use this syntax with the execution configuration here, as we have seen before. And finally, when the kernel terminates, we transfer the results from the device, from the GPU memory, to the CPU memory, also using this CUDA main copy. As you can see already, the difference, the key difference between these two is that the destination array in this case is this D-in, because this is a copy that goes from the host to the device, while here the destination is H-out, that is allocated in CPU memory, because this transfer goes from the device memory to the host memory. Actually, this direction is indicated with another parameter that we have here at the very end, and you're going to see it more clearly in the next slide. Every time that a kernel terminates, the control returns to the CPU. At some point, the CPU might decide to launch a new kernel, offload more computation onto the GPU hardware. It might be the same kernel. There are some programs that are iterative and call multiple times the same kernel, or it might be a completely different kernel. Inside the kernel, as we will see, automatic variables are transparently assigned to registers, to the internal registers in the GPU core that are assigned to each thread running on this core. We also have the shared memory. We have already talked about this shared memory before. It's a sort of a software managed cache or a scratchpad memory where the programmer or the compiler can decide to place some small arrays or some variables that are going to be shared because they are useful to all threads or many threads belonging to the same thread block. And we also have the intra-block synchronization, threads belonging to the same block, which is also and they are also threads that will run on the same GPU core, can synchronize. And this synchronization is done with a barrier, and the syntax for this barrier is these sync threads that you can see here at the bottom of the slide. So going into some more details of the CUDA programming language for you to start becoming familiar with the syntax of these different APIs or library calls, we have this CUDA malloc to allocate a certain number of bytes that are pointed by this D-in, that is a pointer previously declared. We have the mem copy. In this case, is a copy host to device. So from the main memory of the CPU to the memory of the GPU, and the destination is an array, is a pointer in the GPU memory, and the source is a pointer in the CPU memory. As you are already guessing, for the transfers to happen from the GPU memory to the CPU memory, we'll have to change this parameter here to device to host. This is the syntax of the kernel launch, as we have seen before. After terminating our program, we obviously want to deallocate memory. We want to free memory space, so we can use this CUDA free. And also, if we want to make sure that one kernel terminates from the, because for example, one CPU thread wants to really know when a kernel terminates on the GPU, we can use this explicit synchronization, CUDA device synchronize. And this is important because whenever a CPU core a CPU thread launches a kernel to execute on the GPU, this execution is asynchronous. That means that after launching the kernel, the CPU thread, it's free and can continue doing other operations, same as it could simply wait. But if this thread eventually wants to know exactly when the GPU kernel has terminated, it needs to use this CUDA device synchronize. And after the CUDA device synchronize, it can start, for example, using the values and the data generated on the GPU side. Okay, by using these functions and using these library calls, we can start writing our first CUDA code example. And actually, this is the host code example. It's not the main function, but this would be like a function that is being called by the main function, and we call this one backAdd. You can see that it's a vector addition, and here we have 3 arrays, A, B, and C. A and B are the 2 input arrays, and C is the output array, and the arrays are of size n elements. In particular, they are floating point operands. And at the very beginning, you see how we declare the pointers A, B, to arrays A, B, and C in the global memory of the GPU, and we allocate memory for these 3 pointers using CUDA-malloc. In this case, because it's as simple as a vector addition, we allocate the same amount of memory for the 3 arrays. But now, and assuming that the arrays A and B already exist on the CPU memory, we can transfer from this memory area pointed by array A, by pointer A in the CPU memory, we transfer from the host to the device to move the entire input array A from the CPU memory to the GPU memory, and we do the same using CUDA and copy for array B. Then we would have here the kernel launch, as we are going to see in a couple of slides. But after terminating the kernel, we will have to copy back data from the GPU memory to the CPU memory. That's why now the destination pointer is this C that points to an array allocated in CPU memory, and the transfer now, as you see, is from device to host. After moving back, or after copying the results, we can deallocate, we can free all the memory previously allocated on the GPU memory. So the vector addition is our first programming example. It's a pretty simple operation, as you know. The only thing that we know is the element-wise addition of 2 arrays A and B, and we store the results in an array C. In this most simple implementation that we can think of, what we do is assigning 1 GPU thread to each element-wise addition. So this thread here is going to be thread 0 and gets assigned this operation, thread 1, and so on. But now we know that, well, we know that the whole set of threads that execute one kernel is called a grid, but we need to have a way of assigning these threads to the GPU cores, because even though we may have, I don't know, 1 million threads, in the end, we won't have 1 million SIMD lanes available every time for the execution of these 1 million threads. So we need a better way of assigning threads to the GPU cores. And that's why we define or we group threads into blocks or thread blocks or work groups in the OpenCL programming language. So for example, in this very toy representation, what we can do is saying, okay, these 4 threads here compose block 0. These 4 here are block 1, this is block 2, and this is block 3. And the computation that is assigned to each of the blocks is the same computation that we previously assigned to the different threads, but now we know that threads in block 0 are going to operate on these parts of the arrays. Block 1 will operate on this part of the array, block 2, and block 3. And using thread blocks has one key advantage, is the fact that the hardware is free to schedule thread blocks. This is what we call the transparent scalability. Imagine that you have a kernel grid, you have a kernel, you're going to launch a grid of threads, and these threads are grouped into thread blocks. In this particular case, our grid contains 8 thread blocks numbered from 0 to 7. And now imagine that our GPU or device has only 2 GPU cores, right? These that are, you can see here in this simplified representation. So we will need to have a scheduler inside the GPU core that decides when to schedule and start the execution of the thread blocks in the kernel grid onto the cores of this device. And one way, it might be this one. For example, we start the execution assigning block 0 to one of the cores, block 1 to one of the cores. When these 2 finish, the corresponding cores are free, so we can schedule new thread blocks, like, for example, thread block 2 and thread block 3, and so on, until we terminate the execution of the kernel, because all thread blocks have been executed onto the available hardware. By the way, here you can see that we are doing some sort of, let's say, linear assignment of blocks to cores. This is not guaranteed at all. We cannot assume that if we have a device with 2 GPU cores, the first 2 blocks to be executed will be block 0 and block 1, and they are going to be executed concurrently. We cannot assume that at all. As I said before, this is a booked synchronous programming model, so we can only assume that one thread block belonging to a grid, belonging to a kernel, has finished the execution when the whole kernel has finished. So in this point here. The good thing of the transparent scalability is that if now our device has more cores, like for example, this one that has 4 GPU cores, we can, or the scheduler can easily allocate different blocks to different cores. And in this case, we would have 4 different thread blocks running at the same time on the available cores, running concurrently. When these 4 threads finish, or when one of them finishes, the next block will be scheduled. For example, when thread block 0 finishes, block 4 gets scheduled. And as I said before, each block can execute in any relative order relative to other blocks. We cannot assume any order in the execution of blocks. Okay, now let's see how we launch a grid. We have already seen the syntax very briefly, but now we are going to see it with a little bit more detail. Threads in the same grid execute the same function that is known a kernel, and a grid can be launched by calling a kernel and configuring it with the appropriate grid and block sizes. So this is what we call the execution configuration. And as you have seen before, in the kernel call, we will have the number of blocks that are going to be launched on the GPU hardware and the number of threads per block. Normally, these numbers are going to be a function of the amount of data that we want to process. For example, in the vector addition kernel, we have n elements, and we want to assign one element-wise addition to each of the threads. So if we decide, for example, to use 512 threads per block, we will have to launch as many blocks as needed. And this number is determined by the it's a total number of elements and over the number of threads per block. This division will give us the total number of blocks. And the kernel call will be something like this. So now we know that in this part of our host code, what we will have is the definition or calculation of the execution configuration and then the kernel call. And how do the internals of this kernel look? How does this kernel code looks? We already saw this in the previous lecture, actually. Remember, we compared this simple CPU code with the CUDA code, which in the end is very, very similar, not complex at all, because what we have is here is the access to the global memory to read one element from array A, one element from array B, and then we add them and store the result in array C. The only, say, key difference between the CPU code and the CUDA code is that in the CUDA code, we are essentially unrolling the for loop, assigning each of the iterations to a different CUDA thread, and then each CUDA thread, each thread has an own identifier that will tell it where exactly to access. And this identifier can be obtained based on the block index, because as you have seen before, thread blocks are going to be numbered, and also inside each thread block, the threads are also numbered. Just to start summarizing what we have seen, the kernel is preceded by a keyword or a qualifier that is called, that is global to indicate to the compiler that a specific function is a GPU kernel. Inside the GPU kernel, we need to use some indices to identify what's the thread block or what's the thread inside the thread block. And it's also important to know what's the block size as well. So we have special keywords, built-in variables that are here to identify the block index, the block size, and the thread index inside the thread block. So the code would look like this, right? And here what we have is the calculation of the global index that tells each individual thread what elements of, in this case, array A, B, and C, it has to access. So observe that we calculate this index by using the dimension of the block index, and the thread index. So now this I tells every single thread what are the elements that need to be accessed. There is one small thing that we have to add to this simple back-add kernel are the boundary conditions. We have to check whether we need to use one thread or not, because normally we won't have a number of threads per block. So the total size of the input is not going to be normally a multiple of the number of threads per block. So in this case, what we have to do is deciding what's the number of threads that we launch by computing the ceiling of the this division here, where we obtain what's the number of blocks. So here you see that we want to use, for example, 512 threads per block, but we want to round up the number of blocks that we launch to a number of blocks with the corresponding number of threads that spans the whole arrays of n elements. And this simply, the code is going to look like this. Inside the kernel code, what we do is obtaining the index and then checking if the corresponding index is still inside the arrays, is smaller than n. Okay, so regarding compilation, now we have written more CPU code or GPU code. We have to compile before we execute on the heterogeneous system, on the CPU and the GPU. So we are going to have C or C++ code for the CPU, and we have CUDA code for the GPU. And these codes are fed to the CUDA compiler that internally calls the host compiler for the CPU code, and it will generate the host assembly, the machine code for a specific CPU, either an x86 processor or an IBM power processor or an ARM processor. And then on the other hand, we have the GPU code itself. The MVCC compiler, first thing that it does is compiling to an intermediate representation or a virtual ISA that is called PTX and is common to all GPU generations. And then it uses a device just-in-time compiler that compiles to the specific assembly called SAS of the specific architecture, either an Ampere or Hopper or any other architecture. And then that code will run on the GPU. So we have already seen how threads need to access data elements in input arrays, but the very first example we have covered is simpler one, is the vector addition. And for this vector addition, we are just using like linear addressing, the way that different threads are numbered and the way that these are indexed and these different threads access the data structure is in a linear manner. But sometimes we may prefer to use two-dimensional organizations or even three-dimensional organizations, and that would depend on the specific data structure that we are using. For example, images, they are two-dimensional data structures of a certain height and a certain width. Here we have a very simple image. Let's say this 8x8 image is composed by 64 different pixels. And if we want to access the one pixel of this image, we need to know what's the row and what's the column where the specific pixel resides. For example, this pixel here is image 01 because it's in row 0 and column 1, or this one is image 1, 2 because it's in row 1 and column 2. But how are these images in memory? And that's something that we already talked about in our previous lecture. They are going to be linearized, either with a row major or a column major layout. We are going to assume a row major layout. In the row major layout, the row and column of the image tell us or can tell us what's the specific memory address, memory position that the pixel, where the pixel resides. Because our image has a certain width, if we want to know exactly what's the address of one specific pixel, we have to multiply the row index times the width of the image, and then add the corresponding column index. So here we have like, let's say a stride, a distance between the start of one row and the start of the next row. And this stride is essentially the width of the image. In this case, assuming that there is no, we are not padding extra columns or something like that. So this element here, that was element 01, in reality resides in the address 0 times 8 plus 1, being 8 the width of the toy image that we are using in this example. Or this element here is element is pixel 1, 2, and it resides in the position 1 times 8 plus 2, or address 10. So if we are using so the way that we let's say distribute the computation for this image across the different GPU threads or across the different threads that belong to blocks, that belong to a single grid, we would need to use the identifiers of the block, the dimensions of the block, and the identifier of the thread inside the block, as we have seen before. And we can distribute the computation in this image in this way. For example, let's assume that for now our thread blocks are of size 4 threads. So we would assign these 4 pixels to block 0, and then these could be assigned to the rest of blocks. So, but if we take a closer look at the block 0, here we have 4 different threads from 0 to 3 that are being assigned different pixels out of the group of pixels or the chunk of the image that was assigned to block 0. And if we want to exactly know what's the pixel that we are accessing with one specific thread from one specific thread block, we need to know what's the block index, the block dimension, and the thread index. For example, this pixel here would be assigned to a particular thread. This particular thread is going to be thread 1 in block 6. Actually, this is block 0, 1, 2, 3, 4, 5. So this is block 6. And this particular pixel is assigned to thread 1 of block 6. So if we want to know what's the exact pixel, the exact memory position that this thread needs to access, we have to compute this address by using the block index, the block dimension, that in this case is 4, and the thread index inside the thread block. And here it's address or element 25. But we can also have two-dimensional blocks. In this case, we have we define all block sizes and all indices of blocks and threads in 2 dimensions. So here, this could be block 0, 0. These are the rest of blocks. If we take a look at this thread block in particular, this is thread block 2, 1. And inside each thread block 2, 1, we also have a 2-dimensional organization of individual threads. And for example, this particular thread, or the particular thread that we assign to this pixel, is thread 1, 0. So now, if we want to compute or calculate exactly what's the pixel that is being assigned by one thread belonging to these 2-dimensional blocks, we have to calculate the row and the column. For example, for this one here, we first need to take into account what's the block index in the y direction multiplied by the block dimension in order to start where the thread block, the specific thread block starts, and then we add the thread index inside the 2-dimensional block. And this way we obtain the column, and in a similar way we obtain, we can obtain the row, and in a similar way we obtain the column. So for example, this element here is in row 0, 1, 2, 3. As we know, the way to obtain this row 3 is by using the block index in the y dimension. This is block 1. The size of the block is 2 in the y dimension. Block dim.y is 2. And the pixel, the particular thread that is assigned to the pixel is thread 1. So this would be thread index y 0, thread index y 1. And same way we calculate the column. In this case, in the x direction, the index of this thread block is 0, and the index of in the x dimension, the index of the thread assigned to this pixel is 1. So this is how we calculate the column. And once we have the column, we can have, and the row, we can obtain the exact position or exact address of one specific pixel of this image in the memory. Okay, so this is essentially all for now. We will continue in our next lecture. Now we know how we can define grids of blocks, of threads. We know how we can launch kernels to be executed on the GPU hardware. And we know how the individual threads in different blocks can access data that resides in memory. We have seen the example of the arrays in vector addition. We have also seen the example of the 2-dimensional images. Once the code is defined and the thread blocks are defined and we launch the kernel, these thread blocks are assigned to GPU cores, as we have seen as well. And inside the GPU core, remember from the previous lecture, they are decomposed into warps. And these warps are these kind of SIMD units that are going to be executed, or instructions for these warps are going to be executed onto the available functional units like these SPs here that are the regular SIMD lanes that might be, as we have seen in the latest generations, A100, H100, They might be for integers, for 32-bit floating point or 64-bit floating point. We also have load and store units to access memory. We have others like these special function units. And here in the GPU core, as you remember, there is a warp scheduler that goes to the instruction cache and says, okay, now I'm going to execute this particular instruction for this particular warp. I launch it every cycle onto the available functional units. If you want to read a little bit more about the contents of today's lecture, I can recommend your chapters 1 and 2 from the Programming Massively Parallel Processors book. And in our next lecture, we will continue with this introduction to GPU programming and the how to write GPU software by getting familiar with the memory hierarchy of the GPU and the different memory spaces that can be accessed by threads. Threads in the same block can access same data that resides in the shared memory, the on-chip shared memory, but they can also access the off-chip memory, the global memory, where they can share data from, with threads that belong to other blocks in the same grid or to other threads that will belong to grids that will execute later kernels. So this is all for today. Please don't hesitate to reach out to me if you eventually have any questions about the contents of today's lecture or the course in general. Thank you very much for your attention.